Okay, so let's get started. So the last two lectures have been pretty long and intense, so I'll try to keep today's quite a bit shorter, and we'll try to finish early so that we can get started on your spring break activities. So we have assignment 4 out. I encourage you to go look up at the problems online. So there are problems from chapter 4. I think there's 4 problems in the assignment. And the goal today is to get you started on those assignment problems. So why don't you have a look at problem 4.3. Found a better way to make drawings. So problem 4.3 is a pendulum, all right, and the pivot point is moving downwards with a known speed v. So gravity is down. And so you're asked to find the equation of motion for the pendulum. So let me give you a couple minutes to choose a generalized coordinate and write out the kinetic energy for the pendulum, as well as the potential energies. So I'll give you maybe 5 minutes to try and come up with that, and then I'll give you a hint as to how you might do it. Okay, so start by writing out T and V in generalized coordinates. So remember, the velocity v of the fulcrum is a known quantity, so you can express things in terms of v or t if you need. So this velocity v is like a constant, or it is a constant. So presumably the kinetic energy and the potential energy may depend on v. So with that in mind, have a go at writing out those terms. Okay, so hopefully you've had time to think a little bit about this problem and maybe try to find a generalized coordinates. So the first question is, how many degrees of freedom do we have in this problem? How many numbers do we need to specify at a given time t to completely specify the state of the system? So there's only 1 degree of freedom. So at any time t, because I know the position of the fulcrum, right, it's just going to be a distance of vt away from the origin. So at any time t, I know where the fulcrum of the pendulum is, because I know v. I only need one angle to describe the system, or one number. In this case, I can choose the angle theta. That'll tell me where the mass is at the end of the pendulum. So just like a simple pendulum, there's only 1 degree of freedom. So our next step is then to write out the kinetic energy and the potential energy in terms of that degree of freedom so that we can get the Lagrangian. So the kinetic energy will be a half m, and it's always easy to write in Cartesian coordinates as a half m x dot squared plus y dot squared. So we need to know x and y in terms of our generalized coordinates. I'm not going to do the whole problem for you, but I want to get you started on it and then answer any questions if you have any as you go through the derivation. Okay? So I did something devious in the diagram. I made the y-axis point downwards. So we have to be very consistent. So once you draw the axes, everything you do is dictated by that. So let's start by writing the x position of the pendulum. So the pendulum, right, the mass m, has a position x and y. And we want to write those in terms of our generalized coordinates and things that we know. So in this particular diagram, the x position of the pendulum is minus L sine theta, right? So that one was pretty easy. What about the y position? So it says that at time t equals 0, the fulcrum was at the origin. So at some time t, the fulcrum has moved down a distance v times t, right? And that's in the positive y direction. So the y position of the mass is going to be v times t, and then it's even further down in the positive y direction, plus L cos theta. So then you need to know what x dot is. And you need to find out what y dot is. And I really write it out explicitly, y dot is dy by dt. So when you do y dot, you're going to end up with a term that's v plus L cos theta, with the time derivative of that. Okay, so then the y dot term is going to have 2 terms in it, right? And so ultimately you're going to need y dot squared, and so that's going to be something squared, right? It's going to be the 2 terms squared, so you're going to have something squared plus 2 something plus something else squared. And so you're going to have this cross term here that you need to carry around everywhere. Now what about V? So the question is, V is equal to mgy or minus mgy? The potential energy. So you have to be always very, very careful with this, because you have to keep changing the sign of the V term, right? Because it's T minus V, but then ultimately when you do the Euler-Lagrange equation, it's minus di L by di Q. So you have to be very, very careful with the sign. So the potential energy of the mass is minus mgy. Why is it minus? because I did something devious and I put the y-axis going positive downwards. In that case, the potential energy is minus mgy. If y was going upwards, then it would be plus mgy. So the potential energy term will be minus mg times what we had for the y coordinate, which was vt plus L cos theta. So now you just have to be very, very careful with all of the derivatives and not forget anything. So a few hints. Remember, in the Euler-Lagrange equation, you have a d by dt of a di-L by di-Q j dot. So remember, the thing in parentheses is the partial derivative, but the d by dt is the total derivative. When you take d by dt of what's inside the parentheses, if any of the things in the parentheses depends on time, you have to take the time derivative. Okay? Now let me give you the answer. Let's think about the answer. So this is a pendulum whose fulcrum is moving down at a constant speed v. And we want the equation of motion for that pendulum. So the equation of motion is going to be, theta double dot equals something. So can we have an expectation of what it should equal to? Well, the pendulum, the fulcrum is moving at a constant speed. So the fulcrum is in an inertial reference frame. It's not accelerated with respect to itself. So there's no difference between the fulcrum moving at a constant speed or the fulcrum being fixed and us moving upwards with a constant speed. It's exactly the same situation. So the equation of motion ultimately shouldn't depend on v. We're looking at how the rate of theta changes with time, or the rate of change of theta with time. So ultimately it shouldn't depend on v. And in fact, we should get exactly the same equation as you get for a simple pendulum. It's in fact no different than a simple pendulum. Okay? So it's exactly the same as a simple pendulum. So somehow these v's that are going to appear in the cross term for y dot squared ultimately have to cancel. And they'll only cancel if you're very, very careful on how you do your derivatives and you do it correctly. If you do it correctly, it'll work. So let me give you another 5 minutes to work that out and ask me if you have any questions. Any questions working through this problem 4.3? Let's have a look at the next one, which is 4.5. Most problems involve springs or a pendulum. This one has both. Where is it? Hold on. So problem 4.5, we have a pendulum with the spring on it. So you have this rod, the light gray part, it's massless, and the pendulum, the bob has a mass m, which I guess I forgot to indicate on the diagram. And the bead, so the bob, can slide with no friction along the rod. So basically it constrains so that the spring is only stretched in its longitudinal direction. The spring itself has a rest length of L. And I think you have to do this problem for the previous assignment by using D'Alembert's equation. And so it's much easier to do with the Lagrangian. So the first step is to identify the number of degrees of freedom. And so we have 2 degrees of freedom. So you could choose the x and y position of the mass, and that's an acceptable choice of degrees of freedom. Any 2 independent degrees of freedom is an acceptable choice. But we can find a more convenient choice, especially since we want to eventually write out the potential energy of the spring, if we define a variable which I'll call r. Would be the distance of the mass with respect to the origin. So let's choose r and theta as our degrees of freedom. So now it's the same as before, right? We need to write T and V, the kinetic and potential energy, in terms of our generalized coordinates. So let me give you 5 minutes or so to do that. And you guys don't ask many questions, but you should ask questions, and feel free to ask questions. I'm here to help you work it through. I always assume that everybody's doing very well and this is too easy, and I'll keep making the assignments harder and harder. All right, well, you asked a question that I was pretty much going to try to answer. So R should be made of L sine and L cos, and then take the derivatives to make the x and y for t. I would say it the other way around. I would say we need x in terms of r and theta, and we need y in terms of r and theta, and then we take the derivatives. Remember, L here is the rest length of the spring. And it's also a little Lagrangian. I apologize that this comes up almost in every problem that L has two different meanings. But hopefully it's clear when it's still Lagrangian. Eventually I'll review the textbook and make everything lowercase L's. Okay? So it's always easier to write the kinetic energy in the Cartesian coordinates, right? So we have half m x dot squared plus y dot squared. So let's look at x in terms of r and theta. So r just takes the role that L had in the previous example. So the x position in this case is r sine theta. All right? So what we need for t is x dot. So x dot is d by dt of r sine theta. Give me a second here. That thing will go away. Alright. So we need to take the time derivative of r sine theta. So in the previous case, with a normal pendulum where the length doesn't change, we had L instead of R, and that was a constant. In this case, though, R is a function of time, and theta is a function of time. So I have to be a little bit careful when we take this derivative, right? Both R and sine theta are functions of time. So it's the product rule for derivatives. So if I do the product rule, I get R dot sine theta plus R cos theta, theta dot. All right, the first one is F prime, so R times G, sine theta. The second term is R unchanged, and then it's the d by dt of sine theta. So d by dt of sine theta, I'm doing the total derivative, so I'm going to have a cos theta. I'm going to have to do, because of the chain rule, the sine of theta of t, then there's a theta dot at the end. That's sort of why I made the hint up here for the previous problem when you're going to do the d by dt of the di-L by di-qj dot. That di-L by di-qj dot had an extra term in it that when you do the d by dt, you have to take them into account. Okay. That's for x dot. So similarly, you're going to get y dot equals also something plus something. Right, it's just going to be coses instead of sines and vice versa, and maybe a sign change somewhere. Now when you do x dot squared plus y dot squared, the part that you need for the kinetic energy, you're going to find something nice in terms of cancellations, and you're going to get r dot squared plus r squared theta dot squared. Now you should work it out and convince yourself that that's true. But maybe you could have just avoided the whole work and said, oh, that's just the kinetic energy in polar coordinates. Which if you did, I think it's the previous assignment or 2 assignments ago, you would have already derived this. So you derived this for the second time. Of course, that's not surprising, right? Because we literally chose polar coordinates to describe the system. I just didn't emphasize it. But you should be surprised if you don't end up with the kinetic energy in polar coordinates. Okay? That's for T. How about V? Well, there's two potential energies. Let me say V superscript G for the potential energy from gravity. So in this case, we're well behaved, so the y-axis points up, and so the bigger y is, the bigger the potential gravitational energy. So the gravitational potential energy is mgy. So you need to know what y was in terms of, probably minus r cos theta, right? Then we have a second potential energy, which is that of the spring, and we call that V superscript K. So the mass has an energy that's due to the extension or the compression of the spring. So that energy will be a half K, and then the extension of the spring in our generalized coordinates is R minus L squared. Remember, L is the unextended, the rest length of the spring, so R minus L is how much the spring is extended. Alright? And so the total V is the gravitational V plus the spring. Any questions about that? Alright, so I'll let you work on that one a little bit later. Clearly you don't have time to finish it now. Just because I want to spend a little bit more time helping you on problem 4-7. So problem 4-7, I advertised this one in the lecture. Oops. So we have a block of mass lowercase m, and it starts off at the top of a hemisphere. And it slides down without friction. So you can tell that eventually it's going to fall off, right? So the question is, at what angle does the block fall off? And I'll give you the answer. Does anybody know the answer? Or? $90 degrees. No, it falls off before that. So maybe you think the answer depends on R and M and such things, but actually it doesn't. We call that, I guess I didn't know what figures phi, so we call it pi naught. It's actually a weird number, it's 48 degrees. Even worse, 48.19 degrees. So if you haven't done this problem before, it's surprising that you don't need to know any of the numbers and then you get some odd looking answer. 48, not 19. Alright, so let's think about this problem, right? Let's think of it in terms of old school physics, so Newton's second law. And you can obviously solve the problem with Newton's second law. In fact, you might have already, just don't remember. Well, what kind of forces do we have on this body? Well, we have a gravity. Well, let me use a different color. We have gravity. What else? We have the normal force. So what's the condition for the block to fall off from the hemisphere? Well, as soon as the normal force is 0, that means the block is not really in contact with the hemisphere anymore, so it's going to fall off. So when the normal force vanishes, the block falls off. It's more like it's sliding off, I don't know. So somehow we need to do our Lagrangian and everything so that ultimately we can end up with a normal force. So we actually do want a force out of our Lagrangian. And so then we can, solve for when n equals 0, and that hopefully depends on phi, and it'll tell us the condition on phi. Okay, so we want to use the Lagrangian method, but we need the forces, at least the normal force. Remember, the normal force is one of these sort of internal forces. It really doesn't dictate the equations of motion. So when that's the case, we did 2 examples, or 2 times the same example, but we found more and more forces on that example in the notes, and that was the case of a hoop rolling down an inclined plane. Okay. So the idea here is that we want to use constraints plus Lagrange multipliers. So that means we need to use too many degrees of freedom. for a block sliding down a hemisphere, how many degrees of freedom are there? How many numbers to specify where the block is? So you only need 1 degree of freedom. For example, we can use the angle phi. But let's use 2 degrees of freedom, because we know that that will result in using Lagrange multipliers, and hopefully they end up giving us a force, and that hopefully that force is a normal force. So that's awfully random, right? So I could choose phi and x, or phi and y, or x and y. But I want to choose something that ultimately the constraint on that, somehow that the constraint is going to be related to the normal force. So let me choose as my second degree of freedom r. So we'll choose 2 degrees of freedom. R and phi. So we have a constraint. So we choose 2 degrees of freedom plus 1 constraint. That constraint somehow, hopefully, is related to the normal. So we have 2 degrees of freedom, r and phi. What is the constraint equation that tells me that the block is constrained to move along the hemisphere? So try to think of the constraint equations between the r's and phi's that allows you to eliminate a degree of freedom if you wanted to just use the constraint and go and get rid of the degree of freedom before even starting the problem. I'm going to give you a minute to think about that. All right, so constraint equation, and hopefully related to normal force. Well, in this case, it might be trivially obvious what the constraint equation is, but too trivial to be obvious. We added in this degree of freedom r, but then the block is constrained to be on the hemisphere, right? So r is basically a constant. So we have the constraint that lowercase r must be equal to uppercase r, which is the radius of the hemisphere. So we can write that as a constraint as a function of r and phi. And that constraint equation is that lowercase r minus r equals 0. So our constraint equation is really it doesn't depend on phi, and it's simply r minus r. So I'm going to sketch out the solution because you won't be able to fully do it by yourself because of the mathematical trick that you're going to have to do. So let me outline the solution. So the first thing you need to do, hopefully this doesn't surprise you, you need to write T and V in terms of R and phi. Now, you have to build, because we're using this method of Lagrange multipliers, you're going to have to build L bar to be the original L, which was T minus V. And then you're going to have to add in a lambda F. So it's T minus V minus lambda times our function F. And we wrote it as lowercase r minus capital R. So now 3, we're going to use the Euler-Lagrange equation to get something like R double dot equals something. And presumably in here there could be R dots, theta dots, maybe even theta double dots, etc. And then you're going to do the second, or sorry, I called it theta now, but we're calling it phi. And then similar, you'll have the second Euler-Lagrange equation for phi, and you'll have maybe phi double dot equals something. Oh, and there's going to be a lambda in here too. One or both of them will have a lambda. So then you'll have this problem of 2 equations, 3 unknowns. The unknowns, right? You want an equation for R double dot, you want an equation for theta double dot, and you don't know lambda. And so I'll encourage you to go back to the notes where we did this problem twice. All right, so the issue here will be that you need to add in an equation that relates R double dots and phi double dots and lambdas. And so what we found was that you can take the constraint equation, which is R lowercase r equals uppercase R, and you can differentiate that twice. And what you'll find is that R double dot is 0. Now that makes complete sense, right? Our constraint is that the mass is sliding down the hemisphere. So even though we've added in this degree of freedom R, it's a constant. So of course, the R dot and R double dots are both 0, right? And you could have just done it with 1 degree of freedom. But we knew that. The point is we wanted to keep the second degree of freedom so that we could find lambda. So that gives you the third equation. And then you're going to try to eliminate the phi double dot, and you're going to find that you need to eliminate the phi dot, not the phi double dot. Okay, so now you're going to have to use a trick. To get rid of phi dot squared. Let me label the equation. From the R equation and the Euler-Lagrange equation, let's call that 1. You're going to get a second equation from the Euler-Lagrange equation and phi, let's call that 2. And the constraint equation, let's call that 3. you'll need to get rid of a phi dot squared in equation 1. So equation 2, I have no choice but to give you the actual form of it. So equation 2 is going to be phi double dot equals G over R sine phi. Actually, we should write it as minus G over R sine phi equals 0. So here we need from this an expression for phi dot instead of phi double dot. So somehow we have to integrate this. And you can't just randomly integrate it because of the R. So the trick is to multiply this equation by phi dot. So if you multiply this equation by phi dot, you get phi dot times phi double dot. It's not very pretty. Phi dot times phi double dot minus G over R sine phi dot equals to 0. Okay. And then you have to be clever here, and you have to recognize that if I were to take d by dt of a half phi dot squared, then it's plus G over R cos phi, I would get what's at the top. So these two guys are equal. Alright, so d by dt of a half phi dot squared. So d by dt of a half phi dot squared is phi dot times d by dt of phi dot. So it's a chain rule. So it's phi dot times phi double dot. So the first term works. The second term is d by dt of g over r cos phi. Let me pretend like g over r is a constant for now. So then I have derivative of cos is minus sine, and then derivative with respect to time of phi is phi dot. So I get everything that I had above. And then you ask yourself, yeah, but r is actually not a constant, right? R is a function of time. So you could go around and carry out all the terms that are going to have the r dots in them. But then your constraint equation tells us that r dot is equal to 0. So r is in fact a constant. So all the terms with r dots would drop out anyway. So it's true that the time derivative of the thing that I have here in brackets, the half phi dot squared, is equal to the equation above that was multiplied by phi dot. Okay. So now the next step, you have d by dt of this thing equals 0. Well, when d by dt of something equals 0, that thing is constant in time. That's what that means, right? So that means that a half phi dot squared plus g over r cos phi is a constant. Let's call it k. I need to be able to evaluate that constant. So we can evaluate that constant because at time t equals 0, phi is equal to 0, and phi dot is equal to 0. We said that the block starts at rest from the top. So it makes sense ultimately that the final answer depends on our initial conditions. So we shouldn't be so surprised we have to actually plug in some numbers. Right? If you give the block an initial push, it's not going to fall off at the same angle as if you just let it slide down with gravity. So it makes sense, right? It's going to matter. So I have a half phi dot squared, is rewriting the equation, plus g over r cos phi is equal to k. So then at t equals 0, we have the phi dot squared is 0, right, because phi dot is 0. And then we have g over r times cosine of 0, which is 1, and that's equal to k. So k is equal to g over r. So ultimately you're going to have a half phi dot squared plus g over r cos phi equals g over r. And the number that you're going to need is the phi dot squared. And so phi dot squared is 2 times g over r times 1 minus cos phi. And you will need this to get rid of phi dot squared in equation 1. The rest of the problem is rather straightforward, right? You have to write the kinetic energy and the potential energy in terms of r and phi. It's something that we've already done almost twice in the previous 2 problems, so it's a similar strategy. Then you build the modified Lagrangian, so it's t minus v minus lambda f. Then you end up with 3 equations, 3 unknowns. You use this trick here to get rid, or to be able to substitute equation 2 into equation 1, I'm sorry. And then you're left with the ability to solve for lambda. And then once you've solved for lambda, you can solve for the generalized forces. And the generalized forces are going to be, there's only one constraint, and there's 2 degrees of freedom. So there's a Q1R and a Q1phi. So Q1R you'll find is equal to minus lambda di f by di r, and Q1phi would be minus lambda di f by di phi. We already saw that f doesn't depend on phi. We also have the di f by di r dot equals di f by di phi dot equals 0. And so the block falls off when Q1R equals to 0. If you follow exactly the strategy from the notes with this trick, you should be able to get 48 degrees for phi. Let's go back and think of what happens. So we added this extra degree of freedom r, and then we placed the constraint that r is constant. And the fact that r is constant means that the block is sliding along the hemisphere. So that constraint, it does sound like it is related to the normal force. It's a constraint on the block needing to be on a specific surface. And so it's hopefully not surprising that we end up with the normal force as Q1R. But I'll let you work that through. So we needed a somewhat smart choice of additional generalized coordinate for this to work out. And so we thought a little bit about the situation, which is that the normal force is probably 0 when the block falls off. And so then maybe we want to add a constraint and a generalized coordinate that are somewhat related to the normal force. And that constraint this relates to the normal force, is that the block must be along the hemisphere. At this point, it's probably a bit much to expect you to pull that out of thin air. So I helped you with the conceptual parts of the problem, but then I think you should now be able to apply all the math. So let me give you, let's say, 8 minutes until 20 past the hour to sort of sketch out the solution and see if there are any showstoppers. And then after that, I'll work on the next problem, and I'm going to do problem 4.9, and then 4.10 is assigned in the assignment, but it's similar to 4.9. So let me give you 8 minutes or so to try and sketch out problem 4.7 and see if you run into any conceptual issues. Okay, so let me finish today with problem 4.9. Is there any questions trying to work this through? Problem 4.7? You have 2 more weeks, right? It's not due until then. I'll just wait because it looks like Shane is typing a question. So. I assume you're typing a question, right, Shane? So the little bubble is next to your name. Just an easy one. Sense-wise positive, but in the main direction. Yeah. So, what is the potential energy? Problem 4.7. So what is the potential energy in terms of the y-coordinate of the mass? The mass is at x and y. Nope. So V is mgy. Think about it. If so potential energy be bigger as y gets bigger. In this case, y goes up. So the gravitational potential energy when you put something up higher is bigger. So it should be plus mgy. So out here when you do step 1, right, t and v in terms of r and phi, you will have to have written, so you have v equals mgy, so you need to know what y is in terms of r and phi. So let's look at the diagram. when I look at the diagram, y is this distance here. So y is our cos phi, right? So the potential energy is mgr cos phi. It's very, very easy to screw that up, especially since v has its sign flipped just about every time you have to use an equation. It's a different sign. You have to be very, very, very careful. Okay. And it's annoying because it's a shame because it's like one of the first things you write down and your whole problem is wrong if you mess up that sign. Alright, so I want to do problem 4.9 because it highlights some aspects that we're going to see later in the course. Remember, I promised you a deeper understanding of conservation laws, conservation of momentum and conservation of energy. And this one, it just kind of comes out that way. So in this problem, we have a little mass m sliding down a big block of mass m with no friction. However, the big block of mass m, it can also slide with no friction on the ground. All right? So it makes sense, right, that when the little m slides down to the right, big m is going to go to the left. Right, because of Newton's third law or conservation of momentum, right? So how would you solve for the equations of motion to specify lowercase m and big M where they are? So you would maybe do Newton's second law, right? So you have on the little block m, you have a normal force and a gravity. Then on the big block m, you have the reaction to the normal force. On the little block, you have gravity, and then you have the normal force of the ground on the big block. So you should be able to write out the equations of motion using Newton's second law, and it shouldn't be too difficult. Alternatively, you could also look at the system and realize that there's no external forces on it, no friction or anything, so energy's got to be conserved. So when the little block m goes to the right, the big block m must go to the left in such a way that total momentum is conserved. And that will also give you the equations of motion, ultimately. And then you'll have to convert the gravitational energy of the little block to the gravitational potential energy to kinetic energy, and that'll tell you the speed of the little block as a function of time. So it's a solvable problem, right? Without using the Lagrange method. So let's see how we do this with the Lagrange method. And presumably your preferred way of doing it would be with conservation of energy. Okay? But now your preferred way of doing it should be the Lagrangian method. So I'm just going to work through this problem, and that'll be the end of the lecture. So step 1, how many degrees of freedom? Well, I think there are 2 degrees of freedom. And I think that I should be able to specify where the big block M is with respect to the origin, and then I think another good one would be the height of the little block M with respect to the origin. So I'm going to call those X and Y. So I mean X and Y as drawn in blue in the diagram. Okay. in case you hadn't noticed, the wedge, the big block M, is isosceles triangle, right? So it has a right angle. So this angle here, right, is 45 degrees. Similar for the one up here. I'm going to label the position of the small mass. I'm going to call it X sub M and Y sub M. Okay. And then the big block M, I'm going to label it by where its corner is. Right, so its X position is our generalized coordinate X, and then the Y position of the big block is always 0. The big block's constrained to be on the floor. Now we want to write, as usual, T and V in terms of X and Y. So the kinetic energy of the little block is half the mass of the little block times the X position of the little block plus the Y position of the little block squared, dotted. So Ym is in fact Y, so I chose that. So that means that, Ym dot, the thing that goes in the kinetic energy, is simply Y dot. The X position of the little block, I need it in terms of capital X and of X and Y, the blue X and Y, right? So because this is a 45-degree angle on the wedge, this distance Y, that's the same distance as this distance here, which I'll call D, right? Because the angle is 45 degrees, Y equals D. So now the X position of the mass is X, right, the blue X, plus L. So now I'm at where the angle is, and then minus D. Alright, so that's X plus L minus Y. So that was really the only tricky part of this problem. So then Xm dot is equal to, so d by dt of X plus L minus Y is going to be X dot minus Y dot, because L is constant. Alright, so the kinetic energy of the little block M is half lowercase m times, we're going to have X dot squared minus 2X dot Y dot plus Y dot squared. So that's the Xm dot squared, and then we have the Ym dot squared, which is just Y dot squared. Alright, kinetic energy of the big block, T superscript capital M, is going to be a half M. Now the big block, it's not moving in the y direction, and the X position of the big block is our generalized coordinate. So it's already in terms of what we want. Finally, the potential energy. So there's only gravity playing a role here. The big block M is fixed to the ground, so its gravitational potential energy doesn't change. So we only need the potential energy, gravitational potential energy of the little block. So is it plus mgy or is it minus mgy? Well, y is positive up, and the potential energy should be bigger if the thing is higher, so it's plus mgy. Alright? So now part A, we can write out the Lagrangian as T minus V. Alright, so that's T little m plus T big M minus V. So both of the kinetic energies have an x dot squared in them. So let me write this as half lowercase m plus capital M x dot squared. And then I have a half lowercase m. Then I have, let me write it as y, the 2y dot squared minus 2x dot y dot, right? Up here we have 2y dot squared, right? And then we have the minus 2x dot y dot. And then v minus mgy. So let me write our Lagrangian again. Top of the page. So L is a half lowercase m plus uppercase capital M x dot squared plus little m times, well, there's a half that cancels the two in each case. So let me call that y dot squared minus x dot y dot. And then minus the potential energy, which is mgy. Alright, so now to get the equations of motion, we do the Euler-Lagrange equations. So let's do it for x. We need di-L by di-x dot. Alright, di-L by di-x dot is m plus m times x dot. That's the first term. Then we also have this cross term where we have minus m x dot y dot. So we have minus m y dot when we take the derivative with respect to x dot. And so what we need, of course, is d by dt of that. So we have d by dt of di-L by di-x dot. So d by dt of that, the m's are constant. So when I do d by dt of the first term, I have m plus capital M x double dot. And the second term, I have minus m y double dot. And then the last term I need for the Euler-Lagrange equation is di-L by di-x. Well, if I look at L, there are no x's in it, so di-L by di-x is 0. So the equation of motion in x is m plus m x double dot minus m lowercase m y double dot equals to 0. Now let's do the same thing for y. We need di-L by di-y dot. So we have two my dot from the first term, and then we have minus mx dot for the second term. So we need d by dt of that, d by dt of diL by dy dot, so that's 2my double dot minus mx double dot. And the last thing we need is diL by dy. So diL by dy, the only time we have a y is the minus mgy term, so if I differentiate that with respect to y, I get minus mg. So if I put it all together, I have 2my double dot minus mx double dot. If I move that to the other side, I have that equal to minus mg. So we want equations of motion for x double dot and y double dot, and here they're coupled. Two equations, two unknowns. Not so difficult to deal with, so let's just go ahead and do it. So the first equation that we had was that so this is the x equation, right? M plus m x double dot equals equals plus m lowercase m y double dot. All right. Yeah, just take the first box equation here, and I move the my double dot to the other side, so I can find that x double dot is equal to lowercase m over the sum of the masses y double dot. I can put that into the y equation. So the y equation was 2my double dot. Then it was minus m x double dot, so that'll be minus m squared over the sum of the masses y double dot, and that's got to equal to minus mg. Alright, so I can cancel an m everywhere. And I'll factor out the y double dot. That y double dot times 2m minus 2 minus m over m plus m. That's got to equal to minus g. And so we find that y double dot is minus g over 2 minus m plus m. And so if we put that back into our equation for x double dot, so x double dot is equal to m over m plus m times y double dot, right? So it's minus m over m plus m times g over 2 minus m over m plus m. All right, now in the assignment, you're asked to do the same problem, that's problem 410, and instead of a block rolling, sliding down, you're going to have a sphere rolling down. So the main difference in including a sphere is that you'll have to add rotational kinetic energy. So for problem 410, you need rotational plus translational kinetic energy. Now I want to go back and highlight some features of this problem that we just did. In particular, I want to go back to the x equation. Okay? So looking back at the x Euler-Lagrange equation. So the Euler-Lagrange equation, just to be explicit, is d by dt of dl by dx dot minus dl by dx equals 0. So in this case, dl by dx was equal to 0, right? In this case. Remember, the Lagrangian didn't have any x's in it. So when we did dl by dx, we didn't have any terms. So because dl by dx is 0, then the Euler-Lagrange equation reduces to d by dt of dl by dx dot equals to 0. And so then we went and did d by dt of dl by dx dot. But we could have saved ourselves a little bit of work. Because if d by dt of something is equal to 0, then that something must be equal to a constant in time. Alright? So let's go back and look at dl by dx dot. Dl by dx dot was equal to, we have, the first term had an x dot, right? So that was m plus m x dot. And the second term that had an x dot was minus m lowercase m y dot. So what does that look like? So that says m plus, well, not even right. So this thing here equals a constant. What if I write it and I separate out the massive? So I have lowercase m times x dot minus y dot minus plus uppercase m times x dot. What's this x dot minus y dot? X dot minus y dot was the x position of the little mass, right? So that's the same as saying m, the x position of the little mass plus capital M times the x velocity of the big mass. That's equal to total momentum in the x direction. So we've uncovered basically conservation of momentum, and so that's what I want to point out. In this framework of the Lagrangian, those things are automatically built in, or they automatically come out if you want. So this fundamental this concept of conservation of momentum just falls out of this method. It's included in the method. It's not like you have to, in addition, conserve momentum. Momentum is conserved inherently in the way this framework is built up. I thought that was pretty cool. All right. Okay, so that's all I have for today. Any questions? All right, so if no more questions, I hope you guys all have a nice spring break, and we'll talk to you the week after next. Bye.